use this sorting stuff, and this time we'll talk about two types of different sorting algorithms that will be more efficient but also more difficult than those that we have discussed before. So the first one is called merge sort. So merge sort is a sorting algorithm that works by dividing an array into smaller subarrays, sorting each subarray, and then merging the sorted subarrays back together to form the final sorted array. So this algorithm continuously splits the array in half until it cannot be further divided. That is, the array has only one element left. So then the sorted subarrays are merged into one sorted array. So we will use this example to illustrate the process of merge sort. 5, 19, 54, 13, and 46. So first we'll divide this given array into two subarrays. So that will be, we'll divide here. So in the subarray on the left, we'll have two elements, that is 5 and 19, and for the subarray that is on the right hand side, we'll have three elements, that is 54, 13, and 46. Then we'll continue to do this dividing process. So for this subarray, we will divide it again. So it will be two smaller subarrays that only contain one element, that will be 5 and 19. And for this subarray, we'll divide it into two subarrays, that is 54, and then a subarray that contains two elements, that is 13 and 46. So for these subarrays, they only have one element left, and for this subarray, it still has two elements, and we have to divide it again. So there will be 13 and 46. Then we'll start the merging process. So for this subarray, we'll have 5 and 19. So for this subarray, it is already sorted. And then for this subarray, we'll also do the merging process, and we'll be 13 and 46. And then we'll merge this subarray with this subarray, so it will be 13, 46, and 54 here. And then finally we'll merge this subarray with this one, and then it will be 5, 13, 19, 46, and 54. And now this whole array is sorted. And this will be the process of merge sort. It's very simple and very easy to understand. Okay. So here's another graph to illustrate the process. You can know that this array, which contains 4 elements, it is first divided here, and then these arrays are also divided, and we'll have those subarrays that only contains one element. Then we'll combine these subarrays. That is the process of merging, and then after completing the merging process, we'll get a sorted array. So here we are talking about the time complexity of this merge sort. So here we have Tk to stand for the time taken to sort k elements, and we also have Mk to stand for the time taken to merge k elements, because you have two kinds of process. The first is dividing the array, and the second one is merging them together. So we can use this expression Tn, that is here, to represent the total time we needed for the merging process. And then we'll know that you have this also contains t in this expression, because it is a recursive process, and through this expression we can know that the time complexity taken is O n log to n, which is O n log n. Okay, So because the constant terms are usually ignored when we talk about, use the big O notation to talk about the time complexity of algorithms. And so for worst case, average case, and best case, all these cases, the time complexity of merge sort is always O n log n. And so because it always divides the array into two halves and then takes a linear time to merge these two halves. Okay, so now we talk about why we use this merge sort. The first is stability. So it is very stable, which means that it maintains the relative order of equal elements in the input array, and it has a guaranteed worst case performance. So merge sort has a worst case time complexity of n log n, which means it performs well even on large data sets. So this is very rare. Okay, and the third one is called parallelizable. So merge sort is naturally parallelizable algorithm, which means it can be easily parallelized to take advantage of multiple processors or threads. So this is basically talking about the process of dividing and merging. Okay. And here we'll talk about some drawbacks of merge sort. So the major drawback is that it will take a lot of space, because when you divide an array into two subarrays, you have to use extra space. That is, you have to use extra arrays to store these arrays. So you will need a lot of additional memory to store these merged subarrays during the sorting process. And it is not always optimal for small datasets. And because if the dataset is very small, actually there are some sorting algorithms that have actually better performances, like insertion sort. So actually, if the data set is small, merge sort is not the best choice. And after talking about merge sort, we'll now deal with quicksort. So actually, quicksort is a very commonly used sorting algorithms, and in many languages, if you use the sort function, if you call this function that is pre-written by its libraries, I think most of the time it is quicksort. Okay, so in quicksort, it contains a very important process called partition. So the target of partitions is to place the pivot. Any element can be chosen to be a pivot, and its correct position in the sorted array, and put all smaller elements to the left of the pivot and all greater elements to the right of the pivot. So partition is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. So when choosing the pivot, there are actually many different choices for picking them, and it is totally based on your choice. You can choose them freely. There's no difference because you don't know what the random array that is given to you looks like. So normally you will choose the first element or last element or the middle element as a pivot, or you can just choose a random element. Okay, so we use this example to illustrate the process of quicksort. Okay, actually here it is. Page. So here is an array that is unsorted. So we'll use, first we have to choose the pivot. So I will just choose the middle one, for example. So now we have chosen 4 for pivot. And then we have to use two indexes. The first is I, and another is j, and you can just give name freely. So I is from here and j is from here. So now you have to increment I if the AI value in the array is greater than pivot. So 1 is less than 4, and however, so you increment I to here is 0 and then 1, so it will be 1. So now you can know that 8 is greater than 4, and you will mark here. And then for j, it is the same similar process. So you will increment, no, you will decrease j by 1 if the aj element in the array is less than the pivot. So you know that 9 is greater than 4, 5 is greater than 4, however 3 is smaller than 4. So you're here. And then you will swap these two elements. So now you'll get 1, 3, 4, 8, 5, and 9. And you'll note that I is currently at this position and j is currently at this position. Then you will just continue with this process. So you increment I, and then you will compare it with j, and you will find that I and j only differ by 1, and then their positions, they only differ by 1. So you will know that the first pass of this partitioning process is completed, and then you will just divide this array into two parts, two subarrays. And now you have a guaranteed thing is that all the elements in the left subarray is smaller or equals to the pivot you have chosen previously, and every element in the right part of the subarray is greater or equal to the value of the previously chosen pivot. And then you will just repeat this partitioning process. You will choose a new pivot for each of this subarray. And for example, I still choose the middle value, and it will be 3, 5, and then you will increment this I from here to here and j from here to here, and you will find that I is here and j is here, and then you will divide this again, and so you will keep this process until you have 1, 3, 4 here and 5, 8, 9 here, and then you will know that you have a sorted array. So actually, when you divide the subarray, you will know that each of the elements is on the left hand side is smaller than the pivot, and all the elements on the right hand side in the subarray is greater than the pivot. So actually, you don't need to worry that the array is not sorted. So now we will talk about the time complexity of this quicksort. So in worst case, it will occur when the array gets divided into two parts. One part consisting of n-1 elements, and other, and so on. So in worst case, the time complexity is O n squared, because you have to keep dividing the array, and each subarray is, and one of the subarray that you have divided into two is it only contains one element. So actually, you have to you have to continue the process of picking one element out. It's like this. So it is O n squared. And for every case, actually, you have this expression to stand for the time complexity needs, so it's very similar to the merge sort that we have talked about just a few minutes ago, and it is also n log n for its time complexity. So actually for the time complexity stuff, you don't need to actually remember every expression is a detailed time complexity of these sorting algorithms, but you do have to know its worst case and its average case time complexity. In some cases, the best case time complexities, and these complexities are often they often ignore these constants, and they are more kind of generalized, and also they are easier to remember because you don't need mathematics to get all of these complex things. And so for this quicksort stuff, its worst case, its best case is same as its average case, that is n log n. And I think that's all for today's activity, and thank you.